Whoa, this is like a cool little infinity thing. We're gonna talk about. Oh, I don't want to. No, I don't want to do that. We're gonna talk about light bulb brightness today, and kind of predict and explain why certain like why a certain bulb would be brighter than another. So right now I have a little bit of a circuit going on, and we have two light bulbs. Yeah, then remember, a light bulb is just a resistor, right? It resists the charge, and it's going to take some of the potential energy and convert it into light. So it's just a resistor. We have series resistors here, and they both have the same resistance of 10 ohms. So my question to you is pause right now and think about, if I connected this circuit, which one is going to be brighter? Which light bulb is going to end up being brighter? So this is the positive terminal of our battery. So think about it. Hopefully you thought about it. If we connect, hey, they're the same brightness. So my gut, honestly, right? My gut before I learned all this stuff was that, hey, or my gut was saying, hey, this one is going to be, right? This one here is going to be brighter because it's going to have the most current going through here, and some of that current's going to get used up to create light. And then it's going to go through here, and there's going to be less current. So that's why it should be that's why it should be less bright. But the misconception there is that current gets used up when in reality it doesn't. So if I actually show the current, I'm going to show it like with the electrons moving, right? The electrons are going to be moving through the negative terminal away from the negative, and they're going to be moving through this whole shebang. Current or current is just charge per time, and the electrons are kind of like negative charge. So you can't lose negative charge because of conservation of charge. You can't lose electrons. Electrons aren't going anywhere. They stay. What's really being used up is their electric potential energy. So this battery gives them electric potential energy, essentially, and that electric potential energy is going to get used up. But really the current stays the same, and each light bulb is actually going to be using the same exact electric potential energy, right? They have the same resistance. So for each and I'm gonna, oh whoa, this is like a little bit of a spoiler. I don't want you guys stuff. It's gonna stay. Oh no, get it out of here. Get it out of here. I can just clear everything. Really, they're gonna use the same amount of potential energy, because if we think about V equals I times R, the current is the same and the resistance is the same. So they're both going to have the same electric potential difference that they're going to kind of use up, you could say. The same electric potential difference going through both of them. They're going to have the same brightness. Now, really, the brightness is determined by power. So power is equal to, power is really just work over time. And power is, so it's a rate at which at which work is being done, or at which energy is being transformed. So power, the work being done is going to be Q times V, right? That's the electric potential energy drop. That's the work being done. So this is the amount of energy that each of these light bulbs are essentially using over time. So power is equal to QV over time. Wait a second, Q over T. That's current. That's our charge over time. That's our current. So power is equal to current times voltage. I almost wanted to say velocity there. It's equal to current times voltage. So, hey, I have the voltage here. I can plug it in there. So P, I'm going to undo that. I'm going to draw this kind of big. P is equal to, why did I commit? I erase this. It's gonna be hard. Squared times R. Ugh. Not too bad. So I drew that really big. P equals I squared times R. When you substitute IR here, right? V is equal to IR, so you get I squared R for power. So if the resistance is the same, then the current will kind of I don't know if I'd say create the power, but the current is kind of, the power depends on the current. If the resistance is right, so more current equals more power. So they both have equal amount of current going through. Remember, current's not used up. Boom, equal power. Now, let's get kind of disconnect this stuff, and we're gonna get a little bit of a parallel series going on. So, in fact, what I might do, I might this, and then I'll have the wire going through here. Cut this. Is there any way I can kind of? Oh, I gotta follow this stuff. All right, let's. Oh my god, I don't need this. I wish there was a trash can. Actually, I think that's bad for the environment. Okay, I'm gonna take you again. Never mind. Hey, take a look at that. So I'm gonna cut it though. This is a lie. You know, they call me Krish likes being an electrician. I know that, but call me back in the stop show the. Okay. I'm channeling my inner electrician. My god. Come on, I want to make this look sort of. Okay. Parallel. We got a parallel thing going on here. So, in the same vein, in the same sort of vein, which light bulb's gonna be brighter? Think about it. Take your time. Which light bulb's gonna be brighter? Well, it's going to be both of them. Both of them. So they're both gonna be the same brightness, and that's pretty cool. So you might be thinking, well, it's obviously because the resistance is the same, and then the current going through them is the same. But it is true the current's going through them. The current going through them is the same, but that's not always going to be true. That's not always going to be true because the reason is because what they're both experiencing that is the same is the electric potential difference between them. The reason is because if you think about Kirchhoff's loop rule, right? This is one loop, so the EMF is going to equal I times R, and then this loop, the same. They're gonna have the same voltage going through them. So if you think about V equals IR, well, if you have the same voltage and you have the same resistance, you're going to get the same current. So in this case, this equation would be true. But a more general equation would be that power, right? You can rewrite it another way. Actually, I'm not going to actually spoil that. Tell you why. But yeah, V equals IR. They have this because they have the same resistance and the same voltage. They get the same current. This equation holds true. What I'm gonna do, I'm gonna kind of end things here, but I'm gonna let you think about something. If I change the resistance, okay, I make this resistance bigger, it will actually, I could honestly just make resistance smaller. Really. Okay. Make the resistance smaller and it's going to get brighter, and then it gets to the point where, hey, we got a short circuit. How do I make it not on fire? Okay, 0.7 ohms. There you go. If I make the resistance really small, it's going to be really bright. All right. Wait, that's not even what I want. Okay, I was gonna ask what's gonna happen to the power outage if I lower the resistance, but I guess I kind of just gave it away because it's brighter. The reason I wanted to kind of talk about that was actually, yeah, I was going to rewrite it another way. P equals, now, instead of doing P equals I times V, well, I is equal to V over R. You plug in that into there, and you get V, oh boy, V squared over R. They call me, I'm really a graffiti artist. I know how to do both. So P equals V squared over R, and in this case, they have the same voltage, so lower resistance gets greater power. Why? Well, conceptually, if you have a lower resistance, you're going to get more current because of Ohm's law, right? Way more current is going through this guy because for the same voltage, if you decrease the resistance, you're going to get more current. That's kind of the path of least resistance thing. Current always takes the path of least resistance. Just keep in mind, it's not entirely the path of least resistance, is the path of least resistance, but still some current will go through. I make this 0, it essentially animations feature reach essentially. So really cool stuff. Hopefully this stuff was at least somewhat interesting, and this will all be important for my next video. So yeah, thank you for watching. More infinite mirror stuff. This is really, whoa, that's kind of neat. All right, see you guys.